Just recorded it straight from you, live.
I could, I just don't know if I set it up to YouTube on this computer, otherwise I would. All right, I will be right back in and go.
Okay.
Yeah. All right, so we are on time. Good afternoon, everyone, esteemed guests and distinguished colleagues. It is my honor to introduce our keynote speaker for today, PSS Spring Seminar, Dr. Katie Lewis. Dr. Katie Lewis holds a joint appointment with Texas A&M AgriLife Research and Department of Plant and Soil Science at Texas Tech. It was recently announced that Dr. Lewis is being promoted to the esteemed position of full professor of soil chemistry and fertility this year. Congratulations. And Dr. Lewis is a leader in soil, carbon and nutrient dynamics, conservation cropping system, and greenhouse gas emission, obtaining more than 35 million in research grants on this topic in 2023 alone. Dr. Lewis currently chairs the Land Management and Conservation Section ASA and has been instrumental in leading the cover crop management community. Additionally, she has served as a chair of the Great Plains Soil Fertility Planning Board since 2020. Through her dedication to research, service, and teaching, Dr. Lewis has been at the forefront of effort to enhance the agricultural sustainability in Texas High Plains, a mission crucial not only for the state, but for the nation. Her journey in academia has been characterized by an unwavering commitment to advancing knowledge and fostering innovation. Please help us welcome Dr. Lewis to share her insights and expertise with us today. Thank you.
Thank you. That was probably one of the best introductions I've heard. I feel very special. All right, let me get this set up. All right, I'm not going to stand behind the podium. I walk around way too much. So I'm going to stand over here. I'm very excited. Okay, very good. All right, very excited to be here today and to talk to you about what my program and I have been working on with several colleagues across the high plains of Texas, as well as into Oklahoma, on the subject of regenerative agriculture. Here, you want to take over? You can give my slide. No? Okay. All right. So, like I said, regenerative agriculture. I'm going to start, and I stole this from Mr. Kobos here. I think it's very important for us to set the stage for what we're talking about. Elmer Kelton was a world-renowned author. He focused a lot on Westerns, but he said it best in that each new generation tends to forget until it confronts the sobering reality that dryness has always been the normal condition in the western part of the state. What years have been the exceptions? Traditionally, it has taken a strong-willed individualist breed to live in the West Texas region, specifically west of the 98th meridian, especially when that living is tied closely to the soil, as in the case with any of our ranchers and our farmers that we have here in West Texas. So we often get caught up with thinking that because the Carolinas can do it, or because Georgia can do it, that it's going to work here. And that's not necessarily the case. Remember, our normal conditions are semi-arid. We're hot, we're dry, we are windy. All of these things combined don't really put an environment to make cover crops conducive, right? So we have to keep this in mind. And this is actually, this whole mindset is where this project originated from. So myself, Dr. Burke, Dr. Kobos, several of us with the Texas Water Resources Institute had this idea of we need a project that spans the southern portion of the Great Plains that recognizes that things are going to be different here. We can't do things like they're doing it across the US when it comes to regenerative agriculture. So the goal of this project is to intensify agricultural production in an environmentally sustainable manner that enhances agronomic, economic, and community resiliency in the Southern Great Plains region. And this is, to me, one of the the projects that I'm going to hold close to my heart for my entire career, simply because it is a large collaboration. We have 28 project investigators working on this, with all of those investigators having several graduate students, staff members that are involved. And we are 2.5 years into the actual project. And in my mind, going through the last 2 years and the drought that we've had, the exceptionally dry growing seasons that we've had, that I would say are slightly less than what the normal is, we have produced large amounts of data that's going to directly impact the farmers in these regions. So to talk a little bit about Texas and Oklahoma and the Southern Great Plains. So you can see the area that we are focusing on here on the map on the right. And we are focusing primarily on cotton and wheat production, as well as livestock production. And we're trying to investigate how we can incorporate regenerative practices in this regenerative environment to where we can have optimized yields. We don't want to see yield reductions, because we know a farmer is not going to adopt a practice long-term if it's not both economically as well as environmentally profitable. But we also know there's lots of knowledge gaps. Most of the research that's been done on large scales has been conducted in areas that receive more than 16 inches of rainfall annually. And so we wanted to try to address those gaps, because we know if we don't do something now, we probably should have been doing stuff 10, 20 years ago. But if we don't implement these practices now, we're going to continue to deplete our water resources. We're going to see diminishing soil carbon stocks. We're going to have net positive production of greenhouse gas emissions, contributing to climate change, as well as a diminishing profit potential. We know that the Ogallala aquifer is depleting. With that, we're going to have more and more acres being converted into dryland production. And with that, our profit potential is also going to decrease. So before we go any further, we have to understand regenerative agriculture. And if you go out on the World Wide Web, there are so many different definitions. So one of the things that we wanted to do as a project team was to define regenerative agriculture. And so the way we have defined that is the continued capacity of agricultural systems to function in a changing climate that supports soil health, communities, economic output, environmental sustainability, and resiliency to outside threats of those outcomes. And so moving forward, when we think about regenerative agriculture, we want to ensure that we are supporting all of these things whenever we are implementing practices. So onto the actual project that's being conducted. There are 5 main components to this project. The first one, and they're not really in any order here, but outreach is a major component. So we've conducted a series of surveys, which I'm going to discuss some of the results of with you guys today. There is a large modeling team. We have obviously a large field research team that's contributing to both the modeling as well as the economics, and then our extension and education as well. All of these things feeding into the extension and education component. And Dr. Gual, I'm sure you are enjoying the UAS, right? The sensor technology is a major component of this as well. So within these things, we have developed a master soil steward program, which is a set of kits that can be taken to a grower meeting or to a 4-H youth group. They can bring soil samples in, and right then and there, we can run through a set of assessments that are going to provide them information directly about their soil. And so we're in the process. We've conducted 2 or 3 grower meetings to this point, and hopefully in 2024, we'll expand that across the High Plains as well as into Oklahoma. We're utilizing the models to assess long-term impacts of these practices from a soil and water perspective. A big component, so we could talk about conservation agriculture, right? Cover crops, no tillage, crop rotations. But one of the big things that's part of regenerative agriculture is incorporating a more diverse system. So in addition to the rotations and the cover crops, also implementing cattle or goats or whatever sort of livestock into that system. So that's also a large part of this. We plan to, and hopefully with the permission of Dr. Ritchie, implement a course this coming fall semester focusing on regenerative agriculture in semi-arid environments. And we'll utilize what we're learning from this project to go into that course. And then, of course, our economists are working on farm budgets and then determining the potential impacts on those rural communities that we're working in. So I mentioned this was a very large team. And unfortunately, we've had lots of changes to this original list, people changing jobs. We actually have a new faculty member that's going to be joining Texas Tech University here in a couple of months, Dr. Alex Rocatelli. He's coming from OSU, and he is going to be bringing this project with him. So there are things that we're going to start implementing here regarding grazing. But I just wanted to show you, we have objective 1, 2, 3, 4, and 5, the different aspects that I just talked about, but to really illustrate the diversity of our group and the number of scientists that are involved in each aspect or each objective of this project, but they're working on other objectives, right? We can't be in our silos. We have to reach out. We have to provide information, not just to the field components, but the extension and the outreach. So we're all working together collaboratively. And I would say the most important part of this team is our advisory board. Our advisory board is made up of representatives from Plains cotton growers. We have farmer Barry Evans, who's on the call now. We have soil and water conservation districts, NRCS, different commodity groups that are all contributing to this project. They are where the majority of these ideas are coming from. They are pushing the research that we're doing because, in all honesty, in agriculture, if we aren't addressing the needs of the farmer population, what are we doing, right? And so they are driving a lot of what we're doing. So this was our first team picture that we took in 2021, right? Yeah. And I'm about 7 months pregnant at this point. So this project, well, actually, my son is a good reminder of where we're at in this project. I had him about 2.5 months after that picture. And this is where we're at now. This picture was taken in August of 2023. This is including all the new staff that have been brought into the project, the graduate students that are involved. So you can see our team has grown substantially, and all the knowledge that's being brought into this is really amazing. All right, so the first part that I'm going to talk about the survey component and then more of the field research that we're going through. So with the survey, we had 2 main objectives. The first one, to characterize producers in the Southern Great Plains of Texas and Oklahoma through farm and personal demographic information. So who's out there, what are they growing, how long have they been doing this, as well as to determine what the producers see as the major barriers to adopting cover crops across the region. So if you look into the literature, there was a survey that was done sometime before 2020, and what they found to be the major barriers, 49% said it was time and labor that was required to implement these practices. 42% no measurable economic return, 39% said that cover crops will reduce the yield of the following crop. So we wanted to look at this specifically in the Southern Great Plains to see what those adoption barriers were, because again, that's going to be what drives the research questions that we ask. So they mailed surveys. This is being led by Dr. Alan Berthold. This objective is, he is with the Texas Water Resources Institute in College Station. And so he, along with several others, developed this survey. It's sectioned into 6 parts. It's farm demographics, adoption potential, barriers to adoption, reasons producers use cover crop species and varieties, and then the personal demographics. And you can see some of the questions that were asked. What is the type of crop that you farm, approximately how many acres, and then of those acres, how many were irrigated? And then the surveys trying to identify those barriers included things like cost of new equipment, lack of water availability, and then they were able to select from either strongly agree or strongly disagree. We also wanted to know how old or how many years these individuals have been in agricultural production to see if there's a relationship between their resistance to adopt and their age. They mailed out 3,000, or they received 3,000 addresses from USDA Farm Services Agency, and they administered the surveys in 2 separate rounds. So the first round was 1,500 and the second as well. And then there were 3 different versions of the survey. I'm not a social scientist, so the reasoning for that, please don't ask. Maybe Dr. Berthold's on and you could ask him directly. But we went through a series of rounds, 2 rounds, 3,000 surveys that were sent out. This is the respondents that we received. And I think this is very true for any survey. You have high hopes of getting all of these responses back. Of the 3,000 that we sent out, we received 663. So not terrible, right? But of those 663, only 189 of those were actual usable responses. So maybe they didn't completely fill it out. There was something wrong with the responses that made it not usable. So total response rate, 24-ish%. Hi, how are you? And then the usable responses was less than 7%. So again, not a social scientist, but me looking in from a different perspective, I was a little disappointed, but I think this is acceptable, right? This is what we're gonna work with. So the basic characteristics, this goes through the age range. This shows that the majority of our respondents were over the age of 71. That tells me 2 things. One, we have an aging farming population, right? The majority of our farmers are older. It also tells me that maybe there was quite a few of the respondents that weren't the actual operators, but they were the landowners. I know me personally, my husband and I, the majority of our acres that we farm are leased, and the majority of the people that own those acres are definitely in this 71 and over age bracket. Gender, the majority of the respondents were female. And then the percentage of the household income was from agricultural production. And as you can see, I know the colors are a little difficult, but the greatest percentage was less than 20% of their income came from agricultural production. So again, not necessarily the actual operators, but the landowners that were filling out this survey. The educational component is quite interesting. We had quite a few with graduate degrees as well as bachelor and associate degrees. Very few that were less that just had a high school diploma. And then the number of years in agricultural production. Again, a much older age bracket made up the number of usable responses that we received. And then again, what I mentioned earlier about whether or not it was the operators or the actual landowners. And this tells us that the majority of them are owning the land, not necessarily leasing their land. We also broke it down by what crops were being farmed. The majority of that is going to be cotton. The blue line indicates the number of acres that are irrigated for that crop type. So less than half for our cotton, wheat, and milo that are actually irrigated. Corn, no surprise that the majority of all of those acres are going to be irrigated. All right, so now to what's most important and most informative is the actual results. Based on the scale that we were using, the lower the value, the more they agree with that statement. So for example, here we're looking at economic barriers. So cost of new equipment, they more agreed, they tended to lean towards agreeing towards the cost of equipment is too much to invest in implementing these practices versus strongly disagree, sorry. Lack of water availability, that should be no surprise to us as well. They strongly agree that that is one of their major barriers to adopting these practices. High input costs, as well as potential for reduction in cash crop yield. So those are things from an economic perspective that are making people less likely to adopt these practices. From an education information barrier perspective, we were right in the middle. There wasn't a strong direction that anyone was taking as far as strongly agreeing or strongly disagreeing. Now, personal beliefs. So one of the question, or two of the questions that stuck out there were the unwillingness to try something new. They disagreed with that. But again, if the majority of these respondents are the actual landowners, they're going to say that. And then learning about cover crops takes too long. These are things that we've heard or maybe we've read in other surveys that have been conducted that were the leading contributors of people that were unwilling to adopt practices. Now, from a farm characteristic perspective, they disagreed with the fact that the landowner did not allow them to use cover crops. But again, keep in mind, if these are the landowners filling it out, that could be why. And then what the field looks like with cover crops, I've heard that a lot. You know, more of the older farmers, they like a clean tilled field, no residue on the soil surface, but that did not appear to be the reason that they weren't adopting it, and then too much residue to manage. From a finance and policy barriers perspective, the main thing that stuck out that they did agree with was that the incentive programs that are being offered didn't pay enough. The value of the incentive payments wasn't high enough to offset what the cost of these practices are. So it definitely gives us something to work with, right? It gives us a direction to go. We definitely need to utilize the information that we're gaining through this field research to try to change some of the incentive programs, work with Plains cotton growers who's constantly in DC lobbying to try to get some of the incentive payments increased potentially. So from the results that we received, there was a mixed bag. They agreed, they disagreed with what the current literature said. The incentive programs is a definite area that we need to focus on that could potentially increase the likelihood of adoption. And then the water availability aspect is something that needs to be optimized. And that leads into some of the research that Christopher Kobos is working on that we're going to talk about here in a little bit from a field research. So probably the area that everyone in this room is most interested in is the field level processes. I really wanted to touch on the survey component because that is very important when it comes to these large projects where there is a social dynamic to it. There is a reason that people aren't adopting these practices, and that was our goal, to try to figure out exactly why that is. So from a field research perspective, we have replicated research sites across this region of Texas and Oklahoma. We have Fort Cobb, Oklahoma, where we're looking at dryland cotton and wheat rotations with summer and winter cover crops. Goodwell, Oklahoma is their irrigated and dryland site where they're rotating corn and cotton, wheat and cotton, sorghum and wheat. And then they're also including some summer and winter cover crops. Lamesa, Texas, that I'll focus my attention on today is where we're looking at cotton and wheat rotations, cotton with and without a cover crop, and reduced tillage, as well as conventional tillage scenarios. We also have a dryland site that's just right across from the research center out north of the airport. We call it our Glover Farm, where we're looking at tillage rotations with and without cover crops, cotton and sorghum rotations, as well as cotton and wheat rotations. And Katerina will be doing some of her PhD research on some of those plots. Vernon, Texas is where we're looking at more of the grazing aspects of these regenerative systems with and without cover crops under rain-fed conditions. So this is a dryland scenario. And then also Chillicothe, Texas, we have our cover crop termination timing trial that I'm going to spend a few minutes on today talking about that is part of Chris's research project. Okay, so to dive into our Lamesa location, here we have a cotton wheat fallow no tillage system. So what that means is that we grow a cotton crop, we harvest the cotton crop, we plant our wheat crop, let it grow until sometime in June or July. We harvest it, and then it sits fallow from anywhere from, on average, about 10 months. It's going to sit fallow before we come back in and we plant our second cotton crop, our next cotton crop. What we have started doing is implementing different summer covers, or I should say trying to implement summer covers. The problem is that we don't want to utilize our irrigation water to establish those summer covers. And so we are trying to depend 100% on rainfall, and we have had difficulty the last 2 years getting any sort of summer cover established in these systems. We also have a continuous cotton with a rye cover crop using no tillage, and then a continuous cotton winter fallow conventional tillage system. More or less, and I don't really like this term, but business as usual practice across the high plains of Texas. All of these are in multiple irrigation levels. So I have my graduate students here today so they can correct me when I say something incorrectly. But we have 3 different irrigation levels. When we first started this back in 2014, it was a low, a base, and a high, with the base being about 60% ET replacement, the low being 33% less than that, and the high being 33% greater than the base. Now it's what we consider to be a low, a base, and then a base plus a little bit. I don't remember how Wayne phrased it the other day, but it was something, we don't have much water left at the Lamesa location. And so we're trying to manage it. The amount that we're actually putting on is probably less than it was 10 years ago. We've had to narrow down our irrigated acreage on the farm. When I first started, we were probably irrigating 100 of the 120 acre pivot, and now we're irrigating maybe 80 acres of the 120 acre pivot. So very limited compared to what it used to be. So we have these systems. We all know that, you know, the whole idea behind cover crops in a semi-arid environment is the water aspect, right? Dr. Burke worked many years on the water component of cover crops, and the ability of water, whether it be through precipitation or irrigation, is the driving factor behind whether or not that cover crop is going to work. We can do other things from a management perspective, like optimizing the termination timing or optimizing our nitrogen management strategies to overcome those yield limitations. But if you look at the patterns that we have from a precipitation, wind speed, temperature perspective, cover crops will do wonders when it comes to reducing erosion. Because when we have a cover crop in place, those are our windiest months, right? They're going to keep that sand from blowing. But what the problem is that our rainfall, our precipitation doesn't always match up to when we need it to make up that deficit of water that's being created by the cover crop. And so that's something that we're working on. And just to give you a little background, this is lint yield in pounds per acre in those 3 different systems that I mentioned, looking at the base, which is the solid bars, and the low irrigation level that is the checkered pattern. And we have our conventional till system in blue, our no-till cover crop system in green, and then our rotation of cotton and wheat in the maroon bars for both 2022 and 2023. 2022, we saw the separation in our systems that we typically see. This is very common as far as the rotation, increasing yields compared to both the conventional tillage system and the cover crop system. It is not often at this location that was established 10 years ago that we see the benefit of the cover crop in the system. Usually there's no difference between the two. Occasionally there's actually a yield reduction with the use of the cover crop. 2023, and we saw that same trend in both the base and the low water levels. Now in 2023, we see somewhat that same separation, but things were rough. Look how much less our lit yields were in 2023 compared to 2022. And if you're working in cotton, really any crop production system, you saw this in 2023. All right, so moving more on to the soil health aspects of this, because we can't talk about regenerative ag without talking about looking at more of the biological, the chemical, and the physical aspects of the soil. So we're collecting soil samples down to 120 centimeters deep. The first two depths, 0 to 10 centimeters and 10 to 30 centimeters, we separated it specifically at those depths so that our modelers could use the information. Is it DACENT that needs it, or DNDC that needs it to be in 0 to 30 centimeter increments, I believe? Yeah. So the reason for that went back to the modelers. So I tell you that because your planning that you're doing from a field perspective is very important for other aspects of research projects. If we were to have gone out and sampled at 0 to 6 inches, 6 to 12 inches, like we would typically do, they may not have been able to utilize that soil information like they can because we separated it the way that we did. So the involved laboratories, Lubbock, College Station, Vernon, South Carolina, Corpus Christi, and University of Missouri. Our PLFA analysis are being conducted at the University of Missouri. South Carolina was a faculty member, Dr. Yilling, that was at OSU. She moved to South Carolina, and so she's going to continue that work. Breakdown of what we're doing from a soil perspective. It's quite extensive. We have chemical, which would be our routine analysis, pH, EC, macros, and micronutrients. Inorganic nitrogen, looking at nitrate and ammonium. The biological is where it gets really intensive, where we're looking more at carbon and nitrogen mineralization, what the potential is to sequester carbon over a long period, as well as more of the biological activity, looking at enzymes and PLFAs. And Hector Valencia, that's online is going to be doing quite a few of the biological analyses and has already started those. From a physical perspective, we're looking at bulk density, volumetric water holding capacity, and aggregate stability. I'm going to ask a question because I see people dozing off, Dr. Ritchie. I'm just kidding. Why are we measuring bulk density? Main focus of this is carbon, right? If we want to know how much carbon is in our soil, the only way for us to quantify that, to calculate that, is to know what the bulk density is. We don't want just a percentage. We want to actually be able to estimate what the carbon stock in the soil is. So we have to understand that component, as well as we have a soil physicist that's also working on what the implications of these practices are on the physical aspects of the soil. Now where it gets really exciting is the temporal measurements. So looking at greenhouse gas emissions, soil moisture, as well as plant health using a sensor-based system. And so we'll jump into that just a second. So this is soil carbon stocks. So what we did, we measured our percent carbon at all our different depths. This was actually some samples that were collected prior to the start of the research, but it'll illustrate the point that I'm trying to make. So after, I think these samples were collected 7 years after the implementation of the practices, we are seeing separation between our systems. We have greater carbon stocks with our no tillage cover crop system. And what is really surprising is that even after 7 years, we're seeing those changes deeper within the profile. Remember, this is a sandy soil. We're going to have dissolved organic carbon moving throughout the profile. We also have root exudates that are deeper in the profile. So we're seeing that separation. But all in all, we have greater carbon in tons per acre with the regenerative practices compared back to the conventional till. So we're seeing changes, 7 years, right? The amount of change that we're seeing is what is somewhat concerning when we start talking about carbon markets and actually selling your carbon that's being stored in your soil. So with our cover crop system, we're seeing nearly 3 tons of carbon per acre increase with a cover crop compared back to the conventional till business as usual system. And if we're talking on an annual basis, that's a very small increase. The payment currently is maybe $10 per ton of carbon. So we're not talking about very much that a farmer could potentially make if you were to sign up for one of these contracts and start selling his carbon. Now, the question is, we're adding large amounts of carbon to the system. Nick, 4,000 to 5,000 pounds of carbon or that biomass per acre, right? We estimate 40% carbon. That's a lot of carbon that's being added to the system just from above ground biomass perspective. So why aren't we seeing more of an increase in our systems? That's where we turn to our greenhouse gas measurements. We're going to monitor the amount of CO2 in addition to nitrous oxide, methane, ammonia that's being lost from the soil surface to try to get a better estimate or idea of what our carbon sequestration potential is. And so part of Nick's research is looking not just at the nutrient cycling and water storage benefits as well as soil stabilization, but really trying to better understand the carbon cycling dynamics. So we're adding all of this residue, all of this carbon to the soil. We're not seeing much of an increase. So if we can quantify the amount of CO2 that's being lost, we can better understand the cycling dynamics that are going on. So Nick is using the different systems that we have. So we have our conventional tillage, continuous cotton system, our continuous cotton with a rye cover, and then our cotton wheat rotation. He's using a GasMet GT 5000 Terra gas analyzer. So this is an FTIR instrument that measures greenhouse gas emissions from the soil surface in real time. So we take it out to the field. It's a closed loop system where the GasMet is coupled with a LICOR chamber, and it's just constantly every 20 seconds taking a measurement of what the concentration of CO2, nitrous oxide, methane, ammonia, water vapor, and carbon monoxide are. And I think we have the ability to add nitric oxide to that as well. So we're measuring all of these gases, and this is a depiction of what it looks like. So this is real time, starting at time 0. We put the chamber on the collar out in the field, hit start. Actually, the GasMet's already running, but the GasMet starts taking measurements. And from this, we have the concentration on the y-axis. We're able to calculate the flux of CO2 as well as those other gases from the soil surface. And then they sit back at their computers and do a bunch of fancy, not really fancy calculations. They use the ideal gas law to then calculate what the actual quantity or rate of that gas that's being lost on an acre basis per day. And so that's what we're looking at here, pounds of CO2 carbon per acre per day, and then the time series at the bottom. Our different colors that we're using, we have blue is the conventional tillage, green is the cover crop, maroon is the part of the rotation that has an actively growing cotton crop, and then the yellow is where it's fallow. And so what we would expect to see is, well, actually, what would y'all expect to see? That's a better question. We're going to treat this like a classroom. Noelia. I'm going to pick on you. So if you have a cover crop out in the field, so let's take this back to say April. If you have an actively growing cover crop versus a fallow field, where do you expect to see greater CO2 emissions from that soil surface? Well, the cover crop, right? Because you have a plant that's actively growing, it's respiring, it's providing those microorganisms with carbon through root exudates. The microbes are feeding on it, they're respiring, and so they're releasing CO2. So where you have a cover crop in place, you expect to see greater gross losses of CO2 from that soil surface compared back to a fallow system where you have less microbial activity, you don't have active plant growth, and the loss of CO2 from the soil surface. But not everybody thinks about that, right? We think, oh, we're putting a cover crop in, it's going to reduce our greenhouse gas emissions. And if we talk about net losses, that is true, because you have to think about the amount of carbon that's being captured versus how much is being lost. And that's exactly what Nick is doing. So we can compare these rates, and consistently where we have a cover crop in place, we have greater CO2 rate of loss, right? They're going to be greater losses from the cover crop system compared back to the conventional till. Nick, did I miss anything? Nope. Okay, good deal. And it does start to decrease. So as our soils begin to cool in September, October, November, we have less microbial activity. The plants are less active from a physiological perspective. They're not exuding as much. There's reduced root growth, less photosynthetic activity. And so you can see that reduction that we're seeing across the board from a soil CO2 loss perspective. And we see the same trends in both the base irrigation as well as the low irrigation. Now, we take that rate of loss and then we look at cumulative losses over time. And that's what we're looking at here. So starting in June of 2023, same color scheme, we have greater cumulative losses in both, well, actually in our base system, irrigation system, compared back to our conventional tillage and our rotation with and without a cover crop. Now, we take that to our low irrigation, and these are going into February. He just took these measurements not too terribly long ago, but we're not seeing as much separation in the low irrigation level. Less plant productivity, less microbial activity because you have drier soils, right? And there's definitely less separation here between our rye versus our other systems. Plus, there was a tillage event somewhere, we think right in here, and an irrigation event, I believe, that led to us starting to see that separation between our systems. All right, so, and he just changed these slides on me, so. So we have greater SOC in our cover crop system as well as our rotational system. The idea here is try to actually quantify the amount of carbon that's being sequestered versus the amount, or the amount of carbon that's being captured versus the amount of carbon that's being lost as CO2. So again, we're looking at our CO2 fluxes. We have greater CO2 being lost from our rye system versus our others, but yet we still have greater SOC percentages with those two regenerative systems compared back to our conventional tillage system. And when we look at the actual amount of carbon that's being sequestered or captured by the cover crop compared to the amount of CO2 that's being lost, there's much greater carbon being lost than there is actually being captured. So we're not showing the potential that we would hope for to sequester carbon over the long term. It's because of our environment. Minimal frost-free days, hotter environment that's leading to that rapid decomposition of the organic material that's being added and the loss of CO2. So here we looked at this already. These are our cotton lint yields in pounds per acre for our different systems. We are seeing some separation between those systems with again, the rotation producing greater lint yields compared back to the continuous cotton as well, the continuous cotton with and without a cover crop. All right, so the future of Nick's work, he's going to continue the soil analyses and gas measurements. We are going to be assessing this across the region, looking at different practices. I mentioned earlier that Dr. Rocatelli is moving from OSU to Texas Tech. He's going to start implementing some of the cover crop grazing work that we're also doing in Chillicothe at the Newdale farm. And so that's going to be incorporated into this research as well. All right, so I'm going to switch gears. I have a few minutes left. So some of what we're doing is cover crop adaptation. So can we evaluate different cover crops, clover, winter pea, for their suitability in this region. We're working with some breeders that work specifically on clover. And so we're evaluating that here as well as at our other locations. We're also looking at small grains, barley, oats, rye, triticale wheat, legumes. I mentioned those, the clover and the pea, and then mixtures of all of those. And then we've also been doing some warm season evaluations, looking at sorghum Sudan grass, pearl millet, temporary bean. That was one that they were looking at specifically in Oklahoma. One of the really cool things, so, you know, we don't have cows at our research center in Lubbock. That's why we're very excited to have Dr. Rocatelli joining us. But we simulated grazing. So we went out, we planted our cool season covers that included rye, sweet pea, sweet clover, winter pea, and then a mixture of those three things. And not sure what to expect when we simulated grazing versus not grazing, but this is the amount of biomass that was produced between the ungrazed in the blue bars and the grazed. And even if we go out and graze it and we terminate it maybe just a little later than what we would normally, we're still producing 5,000 pounds of biomass per acre. That's a large amount of cover, plenty of cover to keep that in place. So not only are you getting the diversification of the system through adding the cows into the system, but you're also getting the benefits of adding the organic carbon, the protection, the physical protection to the soil surface. Good old rye system. You can't beat rye. It's going to produce the greatest amount of biomass. And if what you're looking for, if your goal of a cover crop is to keep the soil in place and add carbon to the soil, rye is one of the better options, especially one of the more economically feasible options compared to sweet clover or winter pea. And you can see they're not producing a whole lot of biomass, definitely not enough biomass on their own to hold the soil in place. You have to add some sort of grass species. I mentioned the livestock integration. Currently, that's only being done in the Vernon area. What they're including there, they have 15 to 20 acre paddocks. The cover crops are planted ahead of cotton, so in the fall of 21, 22, and 23. And then with rain, we'll actually be able to graze those cover crops. 21 and 22 weren't all that great from a grazing perspective, just because we didn't have the rainfall or the adequate growth we needed to be able to graze those. But then we're monitoring cotton lint yield following that cover crop and grazing the cover crop as well. So now on to Chris's work, looking at cover crop termination. So the whole idea behind this is to develop a model that farmers can use that's going to pull in the plant health, the soil moisture, as well as future climatic predictions, forecasts, to build this model that a farmer can go in, he can say his cover crop is at this stage, his soil moisture is here, and it can give him a better idea of when he needs to be terminating his cover crop. And so we're doing this, I mentioned, both at Lamesa as well as in Vernon. We have small grains, whether it be, is Paul's rye too? Ours is rye and Lamesa.
All rye.
And Dr. DeLon's using rye and wheat. We have it under both irrigated as well as limited irrigation or even dryland scenarios. And we're terminating our cover crop 2, 4, 6, and 8 weeks before planting versus a no cover crop. So we're really trying to push that cover crop to as close as we can to cotton planting. And we're looking at the growth phase, the amount of biomass that's being produced, soil moisture, crop yield, as well as nitrogen availability, because that's going to play a big role in this as well. Not only how much nitrogen is available in the soil, but how much is being taken up by the cotton crop. So this is our traditional window for cotton. So we have our cover crop here, we terminate it hopefully sometime in late March, early April, and then we're planting our cotton crop in May, we harvest, and then we do it all over again, right? And so this is where we're implementing our different treatments. 8 weeks prior to planting cotton, we'll go out and chemically terminate our cover. 6 weeks, 4 weeks, or 2 weeks prior to planting. This is just an image of each of those different treatments prior to terminating the cover crop. Now, what do we see? This is our biomass, herbage mass that's being produced. So we have 12 weeks. This is just, we went out, took a sample to see how much biomass was there. You can see at this point in time, we hadn't had a whole lot of rye production, rye growth. And it's not until usually sometimes late February, early March that we really start seeing rapid growth in our cover crop, because that's when the soils are warmer, we have warmer air temperatures. And then the amount of biomass for each of our subsequent termination timings. Anybody wondering why we see that decrease there? I did. We had to think about it a little bit. My thought is that, or our thought is that this is the point in time where the rye is starting to go into reproductive stages. And so it's starting to senesce some of its vegetative material. And so that's why we see this decrease. Here, we probably had an irrigation event, or that's when it started raining in 2023. And so it really started taking off as far as growth goes again. And then really cool part of this is monitoring soil moisture. So here we're looking at soil depth along the y-axis, and this is weeks prior to planting our cotton crop, which would be right here at 0. This is our 8 weeks. So this is about at the pre-boot stage of our rye cover crop. You can see we terminate, and for all 4 of these scenarios, we have more dry conditions. The red indicates more dry, the blue is a wetter soil. And it takes a good while. We have rainfall event or irrigation event that start making up that deficit that was created by the cover crop. But you can see with each one of the subsequent terminations that we stay drier longer, which would be expected. You're not terminating until later. The soil is much drier. Where we are terminating at 8 weeks, we're making up that deficit. You have better conditions for planting a cotton crop. And this is all compared back to our no cover control, much wetter environment. But what you'll notice, regardless of when you're terminating that cover crop, they're all still relatively dry at the surface, right? So it's gonna take that irrigation source to be able to get a cotton crop established. What is more terrifying though, Dr. Ritchie, would you want to plant a cotton crop with this dry of conditions throughout the soil profile? Absolutely not, right? That's a pretty big deficit to make up throughout that growing season. This is lint yields from 2023. We really didn't see any separation at all between our termination timings. I think it was just so dry in 2023. It wasn't giving us the conditions to really see some separation between those or amongst those treatments. So again, remember the end goal of this is to try to build this model that is going to be farmer friendly, that they can take to the field. They can put in whatever their growth stage is of their cotton crop. They can get plant health status, as well as soil moisture information and the weather forecasts as well, to build this tool that tells them when the optimal time is to terminate their cover crop. Real quick summary, and I think I did pretty good on time, right? All right, so just to recap, so we are evaluating these regenerative practices across soil textures. Today, I just visited with you about our Lamesa location that's more of a sandier soil, more intense growing environment just because of our limited irrigation capacity. But we're looking at this across Oklahoma as well as more clay soils across the region. And with all of this, we want to develop the tools that farmers can use. We want to develop the educational materials and are developing the education materials for developing the course that will be taught here at Texas Tech and PSS, as well as at A&M and College Station, West Texas A&M, and Oklahoma at OSU. I don't know who's going to teach it now, but they'll figure that out. So we're developing that. The Master Soil Steward program is also a major component of the outreach, the education. And again, one of the big things that we want to try to encourage is changing our incentive programs or cost share programs? With this information, can we take that to NRCS, to USDA and help change those things for farmers, have some influence over that? So with that, I'll end there. Love to take a couple of questions. We have about 5 minutes. I will say that this is our lab website. Most all the presentations that we give are loaded onto the website. So if you're ever curious, you can go on there, check it out. Is that a QR code still? No. We also have a project website, South Plains Region Ag, where hopefully we'll become more active at posting things. So with that, thank you all very much for your attention. Y'all are a great audience. I'm happy to take any questions.
Okay, thank you. Thank you for the exciting topic and presentation. And throughout my career, I've heard several different terms about agriculture, like sustainable agriculture, climate smart agriculture. Now we see regenerative agriculture. What's the biggest difference?
Whoever's pushing it. If we're going to be real honest. No, so I think they all take a slightly different spin. It's what's really driving that topic. So I always go back to the soil health example. So it's been everything from soil tilth to soil quality to now soil health. And it's really always, it's always been about the health of the soil, right? It's always been about the overall quality. How well can that soil function for your end goal? And I think regenerative agriculture, climate smart agriculture, it's all the same concept, just with a different, slightly different view on it, I guess. They all have the same goal of being sustainable, right? Yep, great question. Yes, sir.
Very good, Katie. I think, do you know anything about if there is any kind of certification program for regenerative agriculture also? Because I think
Yes.
I have heard about it.
Yes.
Like organic agriculture, there are certifications for regenerative agriculture also, so that farmers can get some premium on it.
Yes. So, and that's, I'm sure a lot of you have heard about the climate smart grants that were funded last year or the year before. So that's really what that is going towards. And there's all sorts of different incentives. So there are some programs that are offering incentives very similar to what USDA does, where they'll pay for a practice. There are other programs where they're actually putting a premium on a bale of cotton. So there's lots of different options. There are also different options for how you're getting that crop certified as regenerative or climate smart. So you can use things like the trust protocol, the cotton trust protocol. That's one option. There's BCI, the Better Cotton Initiative. That's also a certification program. Some of the newer ones, Joseph, you may have to help me. Regen Agri is one of those that is becoming more popular. I know there's another one, but I can't think of the name. But there's several accrediting type options there. Do you remember the other one? Yeah, it's a farmer-based program. If I think of it, I'll email y'all.
Thank you.
Yes, sir.
Thank you, ma'am. Nice presentation. Actually, my question is, this Texas area was once like a commercial cultivation, like.
I'm gonna have to get closer. I can't hear. I'm sorry.
It's in this area, like a cotton sorghum is a cash crop, commercial crop. And if we look from farmers' point of view, they are more attractive about the economic resilience as compared to the climate resilience. Because climate resilience is more towards for sustainability, for policy level or the state wide. But for adoption of these techniques, I think you already showed some ideas. Are you thinking farmers can adopt this technique quickly, or they will need like much more time?
Yeah, that's an excellent question. So the question was, for those that are online, is will farmers be able to more quickly adopt some of the regenerative practices and see the economic benefit? And I would say that that's the goal of this project, right? Is we're trying to optimize those practices so that there's not any sort of penalty on their profits when they start implementing them. And we don't know unless we try. And so this is all about trying to figure out what works. Are there any questions online? Any other questions from the audience while we're checking that? Dr. Ritchie, I can't believe you don't have a question.
Oh, I just didn't want to take away opportunity. So out of curiosity, because I imagine that the values of carbon that are left in the soil through these practices are essentially the stable carbon left over, because if it wasn't stable, the microbes would have used it. And I noticed the patterns of your cover crops and the gas plugs followed the same pattern as this increase in stable carbon fraction. Have you looked at the relative magnitude of what you're getting in terms of the carbon flux and compared it with the amount of stable carbon that we're adding? And if so, do we overestimate or underestimate how much carbon we're adding to the soil through that?
So I would say that we're likely underestimating, and especially with what we presented today. So we're not, at this point anyways, not quantifying any below ground carbon. And the roots are going to contribute more toward the stable carbon that you're mentioning. Part of what Nick is going to be doing is separating carbon out into the different fractions and looking at what the fractions are that have the longer half-life. How long are those pools of carbon going to stick around, and then compare back to our total carbon and the amount of CO2 that's being lost. I don't know if that answered your question, but yeah, we're definitely investigating the stable components of the carbon, soil carbon. Nick, you have lots of work to do. All right, well, thank you all. I'm sure everyone is ready to get back to class and doing homework and but feel free, please. My contact information's up there. If you ever have any questions, thoughts, anything you want to visit about, I'm always available and would like to talk. Noelia might say I'm not always available because I've been traveling a lot, but definitely cell phone. You can call me, text me, email me, whatever. So thank y'all very much.
Oh my God. It's so It's 5 years. I know. I'm in
No. We were just doing that like root terminating of the simulation and all. But the goal would be integrating the cattle
At a moment
before terminating. If we can have enough not having any internal store that's to be able to manage the cost of having that same recovery.
Work on the